The talk is quasi-local horizons and black hole thermodynamics. But let me first start with the question whether black holes are truly or really thermodynamic systems, or who even question this claim. But unsurprisingly, I think this is not the right question to begin with. And this is actually no more than what Carnap said, right? Any meaningful metaphysical question concerning the ontology of a concept should not be framework independent. And the theoretically meaningful question should be within the framework. However, in black hole thermodynamics, there does not yet exist a generally accepted or fully satisfactory framework for black hole thermodynamics. And without specifying in what sense and within what framework one is asking this sort of question, I think the claim is null or meaningless. So in this sense, I take this talk to be motivated rather to explore ways in which a framework of black hole thermodynamics can be developed with the appropriate choice of concepts or notions and a set of rules which can be used to formulate the ontology of black holes as thermodynamic systems. And to do so, I need to draw insights both from black hole physics and from the theory of thermodynamics. But is there any empirical evidence suggesting that observational phenomena of black holes violate the principle of thermodynamic behaviors of physical systems? And the answer is arguably no, because black holes are challenging to manipulate, let alone to observe their interactions in ways that will yield sufficient data to test such claims. Nevertheless, the prevailing consensus, I think, in both physics and philosophy holds that black holes are thermodynamic systems. So this thesis actually was inferred from an analogy or the resemblance, as pointed out yesterday in Katrina's talk by Doherty and Callender. And the thesis was inferred from the fact that various mathematical, physical, or simulation-based studies of black holes reveal that the principles and regularities governing black hole mechanics formally and physically resemble those attributed to ordinary thermodynamic systems. And the classic works include, for example, Bardeen, Carter, and Hawking in 1973 and Ward in 2001. So the question is, on what grounds then will anyone reject the proposal that black holes are thermodynamic systems? And I think there are reasons. First of all, there have been recent refractions in the foundation of thermodynamics, and they have deepened our understanding of what one could possibly mean by a theory of thermodynamics and its relation to statistical mechanics or its application in the other theoretical contexts in physics. And these works are mostly done by the scholars in the audience. And the second line of reasons is that the black hole physics also is an evolving field with ongoing efforts to refine the theoretical formulations of black holes and their underlying mechanics. The essence of those above reasons is that our understanding of scientific practices and theories is not static. Rather, it's evolving and dynamic with contents and boundaries subject to change. Therefore, the evolving understanding of the foundations of both fields affects the degree to which the resemblance or the analogy between black hole mechanics and the thermodynamics is established, thereby influencing the inference from this resemblance. So the overview of this talk, first I will give a very brief review of classical black hole mechanics and discuss in what senses they establish the analogy to the thermodynamics. And second, I will discuss the recent criticism by Doherty and Callender against the black hole thermodynamics and talk about some responses by Wallace. And then I'll point out there is still one remaining issues to be addressed. And then I will put forward my argument of this talk. Then I will go to discuss what is the tool that I will use to address this remaining issue, namely a framework of quasi-local horizons, and then we'll discuss the quasi-local horizons and its black hole thermodynamics on them. Then I will go to the conclusion with some thoughts. So first, let's talk about black hole mechanics, classical black hole mechanics. I will use one quotation from Chandrasekhar, one of the pioneers of black hole physics, to start with. He claims that black holes could possibly be the simplest and the most perfect macroscopic objects in the universe. And they presented a formal relationship between laws of black holes and the thermodynamic laws. I picked four important results in the black hole mechanics. First, there exists the uniqueness known for no-hair theorems and conjectures, saying that all possible classical stationary black holes can be exhausted in the exterior field by only three parameters. And second, there is a set of stability theorems, which shows that any small data perturbations of stationary black hole would decay exponentially fast, implying that a perturbed black hole returns to its original stationary configuration. And third, for a black hole spacetime which is stationary and asymptotically flat, one can define the quantity, it's called surface gravity of the Killing horizon. And this surface gravity must be constant on any Killing horizon. And fourth is that the area of any classical black hole is non-decreasing, proved by Hawking. Combining the uniqueness result and the stability theorems, it can be seen that a classical black hole has a uniquely defined equilibrium state. And if a black hole is perturbed away from its equilibrium, it will spontaneously equilibrate and evolve toward that stationary state. Therefore, the equilibrium as a stationary solution of a black hole is a thermodynamic equilibrium, satisfying the so-called minus first law of the thermodynamics that's formulated by Braun and Uvink. And second, the constant surface gravity on event horizon of an equilibrium black hole mimics the temperature of an ordinary thermodynamic system in equilibrium. So this mimics the zeros law. And third, the area law a la Hawking suggests that the area of the event horizon plays a similar role, similar non-decreasing role as the notion of entropy does in thermodynamics. Therefore, it mimics the second law of thermodynamics. And most importantly, as shown and suggested by Bardeen, Carter, and Hawking, and among other physicists, if a stationary black hole is perturbed, the varying relation between its parameters, the mass, angular momentum, charge, and the area, satisfy the following relation. And this relation has precisely the same form as the first laws of thermodynamics. Therefore, with the equilibration process and the unique existence of the equilibrium states for classical black holes, and the formal similarity between the laws of black hole mechanics and the laws of thermodynamics, the resemblance or analogy between black holes and thermodynamic systems has been initially established. But in the recent paper, well, actually 10 years, by Doherty and Callender, they want to argue that while this analogy may not be more than formal. In this talk, I particularly consider the first two lines or two kinds of criticism on black hole thermodynamics by Doherty and Callender. The first of criticism is that they argue there are some physical disanalogies between stationary black holes and ordinary thermodynamic systems, including concerns on the no equilibrium with relation and no non-extensivity, etc. And the second line of criticism focus on a more fundamental concern, which on their view forms a major tension in the analogy. They argue that there are no unproblematic alternatives to the problematic global notion of event horizons in black hole thermodynamics. I will say more about this criticism shortly. So on the physical disanalogies, they say that no thermodynamicist, however, would regard mere constancy of a quantity to express the zero law. The constancy of the surface gravity of black hole is the mere consequence of the real zeros law. I think they get the point, because to express the full zero law, one needs at least three systems that can be in equilibrium with each other, with the equilibrium with relation being transitive. But if, strictly speaking, in GR, if one takes the counterpart of black hole equilibrium with its stationarity, the relation cannot exist, because any black hole cannot, strictly speaking, be in stationarity with another. And second, extensivity of black holes. They argue that the area law implies that even if two black holes identical in their temperature merge into one, the result black hole will have a larger area than the sum of the original two. This is on their view contrary to thermodynamics. But in David Waller's responses, I will not go to the full detail of the paper, but I strongly recommend the audience to read the paper. So the main line of argument is to argue that, well, in order to fully working out the black hole thermodynamics, one need to take the semi-classical Hawking radiation into account. And together with the membrane viewpoint, which is a framework by Throm, etc., based on the stretch horizon. A stretch horizon is defined slightly above the event horizon at the proper distance, small proper distance. And with the associated fiducial observer, which are observers that are stationary to black holes, with that, he argues that thermal contacts are achievable for a stationary black hole. And stationary black holes have well-defined equilibria and equilibration processes, and they obey the zeros first and second laws of thermodynamics. For example, to construct those thermal contacts, I will just briefly mention some of the physical scenarios. For example, in James York's work in 1986, he considers a toy model in which one put a reflexive cavity around the black hole. And he shows that if the reflexive cavity has the radius of the cavity is less than 3 gm divided by c squared, then he showed that there is a minimum of the free energy of black hole, so that it gives rise to a stable equilibrium of black hole and its environment of its radiation. And also, in Waller's paper, he discusses a simple way to put two black holes into thermal contacts in thermal equilibrium. For example, you can put one black hole with a very large distance from the other one inside a very large box. And the box will fill up with radiation at an intermediate temperature between the two. And so the heat will flow from the hotter body into the radiation and hence into the colder body. I mentioned this because in this scenario, the time scale is really what matters, because in this two black holes in the box case, the decay time scales for the binary black hole mergers scales with the fifth power of the separation, but the radiating black hole to equilibrate with its box scales with the cube of the box size. So up to approximation, it's okay to construct such thermal contacts. And this is actually exactly what Ted Jacobson once said in his discussion of black hole thermodynamics. Quote, I think equilibrium is a question of time scales, end of quote. So discussions of thermodynamics in various contexts should pay enough care of the time scales to which thermodynamics is applied. So concerning the non-extensivity, it is certainly true that most ordinary thermodynamic systems are extensive, but black holes like strong self-gravitating systems, which we also saw in Patricia's talk yesterday, are non-extensive systems. And the thermodynamics should actually not only apply to the extensive systems in general. And concerning no equilibrium relation, as we just discussed, thermal contacts are achievable for semi-classical quasi-stationary black holes within a suitable time scale. So to a large extent, I think the first line of criticism from the physical disenergies by Doherty and Callender is satisfactorily applied. But there still exists a second line of criticism, which I call the remaining issue. It's called the fundamental tension by them in black hole thermodynamics, and I will construct the criticism in the form of a dilemma. But first, in the paper, they argue that The event horizon is a teleological and clairvoyant notion which lacks the properties that an event horizon would have to bear thermodynamic features of black hole. And hence, it is inadequate to the task of fully working out the black hole thermodynamics. But on the other hand, after a survey, they argue that there are no quasi-local horizons that can play all the roles required. Therefore, a fundamental tension in the analogy concerns what are the systems in black hole thermodynamics supposed to be. And they conclude that neither global nor quasi-local horizons work to successfully characterize the thermodynamic systems of black hole. And I call this criticism a remaining issue because, note, even though I think Waller's responses are successful, the main use of the membrane viewpoint and the stretch horizon is still dependent on the notion of event horizon. Therefore, in this sense, the second criticism is a deeper one. So here is my main argument. In order to address this second argument, second criticism from Doherty and Callender, I will show that first, there is actually a preferable framework of quasi-local black hole horizons in terms of the isolated and dynamical horizons by Ashtaka and Krishnan. And second, the thermodynamic laws and their interpretations are achievable on those quasi-local horizons. And third, the framework actually strengthens black hole thermodynamics in deeper physically meaningful aspects. Therefore, in supplement, like being supplementary to Waller's arguments, I argue that black holes are thermodynamic systems in the fuller sense. So let's go to the framework of quasi-local horizons. First, I think that Doherty and Callender's criticism on the event horizons in the context of thermodynamics is actually right. Here, I want to give more motivations to supplement their argument against the event horizons in this context. An event horizon is generally known and defined as the boundary of the causal path to the null future infinity. And its location can only be known after the knowledge of the whole space-time has been acquired. So it's a teleological aspect. In practice, and for a finite observer in space-time, the notion of an event horizon is of little use because of its global nature. And in the context of black hole thermodynamics, this concept becomes more problematic due to their clairvoyance, non-local features. When considering a scenario in which a structured black hole interacts with the surroundings, such as by absorbing matters or energy, which can be modeled by the Vedia in Going metric, the event horizon may originate and expand within a region of flat spacetime where no infalling matter or energy is present. We can see that in the shaded region in Figure 1. And in addition, in a recent full quantum gravity calculation has been suggested that in nature, there should not exist any event horizon, in a slogan that nature abhors an event horizon. Because unlike the Penrose diagram of a collapsed spacetime, where the event horizon intersects with the future null infinity, the Penrose diagram of a full quantum gravity spacetime, this is the example of a black hole to white hole transition. In that scenario, it has no such intersections and hence no existence of an event horizon. And also, please allow me to bring to the foreground a third-hand quotation, which I found in Ashtaka's recent paper. As Matt Visser reminded us in his talk in the GR17 conference in Dublin, Hawking emphasized that a true event horizon never forms. In addition to the complaints about event horizon, there are some positive and physical motivations toward a new framework. The first, concerning the area law. The classical area law by Hawking is a qualitative result, but we might want a law that has the explicit and the quantitative form, because by having the quantitative form of area increase, we can know better. We have better control of the area increase due to energy change from different contributions. And second, on the equilibrium for stationary black holes, in the classical black hole thermodynamics, a time translation Killing vector field is required everywhere, and it is actually too restrictive. in more realistic scenarios, we might only want to require the intrinsic geometry of black hole horizons to be time independent, whereas the geometry outside can be dynamical. And third, the stationary black hole thermodynamic first law needs the global assumption of symptotic flatness to define, for example, the mass and angular momentum at infinity. But we also might want to get rid of it and defining all the terms only at the horizon.
Can I ask you a question?
Yes, please.
I'm sorry, I don't know if I can ask questions during your talk. I'm confused about number two. Isn't the in the case of Schwarzschild, isn't the killing vector field inside not even time-like,
Well,
space-like?
yeah, I mean, when I say this, I mean, even the outside, if stretch black hole exists everywhere. But as I said, we don't want that condition very strong conditions because actually the geometry outside the black hole can be dynamical. We don't require the killing vector field exists everywhere outside the black hole. I mean, you are right that, well, it could become space-like or whatever, or null-like on the surface. But here, I mean the outside, everywhere.
Okay, sorry. I get confused between like stationary and static and everything. Just
Yeah.
thank you.
So to develop the quasi-local horizons, the framework of whatever quasi-local horizons, the very basic notion is called the closed trap surfaces, which is a notion proposed by Penrose to address. It was proposed by Penrose to address the concern of singularity due to global symmetries in exact metrics. And closed trap surfaces refer to the set of closed compact space-like two-dimensional submanifolds on which future directed outgoing light rays converge in both directions locally. And the right-hand side picture is from Hawking and Ellis' book, in which it nicely illustrate how to characterize a trapped surface. So according to this picture, you can see at some instance, the sphere T emits a flash of light, and at a later time, the light from point P forms a sphere S around P, as shown here. And the envelopes T1 and T2 form the ingoing and outgoing wavefronts respectively. If the areas of both T1 and T2 are less than the area of T, then T is a closed trap surface. It's just a more intuitive picture. But closed trap surfaces are space-like two surfaces, and they are locally defined, and they signal the geometrical effect that leads to the black hole formation. So trap surfaces are very useful to further define any sort of quasi-local horizons. But here I want to mention something in between the event horizons and the true quasi-local horizons, which is the apparent horizon. Apparent horizon is defined by the marginally outermost trap surface. It is, on one hand, a quasi-local notion because its location depends, or in order to track where it is, it depends only on the data local on the surface. However, an apparent horizon is also foliation dependent, and its definition, at least according to Hawking, requires a Cauchy surface, which is global notion. And if one chooses a different foliation or even just wiggle the chosen foliation slightly, the new outer trap surfaces may appear and the older ones may disappear, showing there's a property of non-consistency. I know this may seem a little bit confusing because I just said that trap surfaces are locally defined two surfaces. Then why is the apparent horizon not local? I think to understand correctly, the key is on the concept outermost. It's a result of comparison. And to use the apparent horizon as the boundary of a black hole, one needs to compare with marginally outer trap surfaces, which one is the outermost one. And this comparison is only meaningful when all the candidate surfaces lie within the same space-like hypersurface, namely a foliation. And without this global perspective, the sitting only locally on the trap surfaces, there's no natural way to compare two surfaces to decide which one is outside the other. And the reason why I I discussed this parent horizon also because it can help us to better understand what is really at issue in the second line of criticism by Doherty and Callender. Here's a quote from the paper, which which shows clearly their concern, in my opinion. They say the foliation independence is tantamount to reality in a relativistic world. The laws of black hole thermodynamics are foliation independent, so it would be strange, to say the least, if the physics they describe is bound to a choice of space-time slicing. Actually, it took me some time to understand what's going on here because to some extent, yes, foliation dependence is a very desirable property, but as we just said, they criticize event horizon because event horizon is a foliation dependent notion and it's not tantamount to reality, so it's not a sufficient condition. And also, I don't think it's a necessary condition. But the most interesting comment is on the second sentence. Well, in my opinion, I think the concern is not or should not be about the contextualism as a form of observer dependence of doing thermodynamics on some foliation, which is, I think, completely fine, as pointed out by, for example, Eugene's work in 2023, along with Wayne's and Robertson and Pronko's work. And we can certainly do thermodynamics of black holes if we could successfully fix a choice of foliation so that the parent horizon is stable and persistent enough. And also, in other words, actually the thermodynamics should be seen as I was taught, that should be seen as means relative, but it does mean that it's subjective. I think the real problem is rather about the consistency or stability of the parent horizon, for example, to track the thermodynamic processes of black holes. And for example, an apparent horizon for an observer by fixing a foliation choice could suddenly cease to exist for the observer, or may have a sudden jump, so the observer loses track of it. And that's, I think, the concern on the consistency or stability of some notion of horizon is the real issue. So now I jump into introducing and discussing a quasi-local framework by Ashtaka and Krishnan. The presentation will mainly be based on their 2004 work, but there are some recent developments. For example, the Kozinski and Booth paper, which try to give a unified version of different quasi-local horizons. And there are developments of the quasi-local horizon in terms of Ashtaka and Krishnan in, for example, numerical studies or a more deeper studies toward quantum gravity. And in order to have this framework, there are two sets of quasi-local horizons. One is for the null horizons, as represented on the right-hand side picture here. And the other set is for the dynamical, hence space-like horizons, connecting those null horizons. The null local quasi-local horizons represent the local geometry at equilibrium, but the space-like horizons here represent the evolving black holes that connect the null horizons. So for the first set of null horizon, quasi-local horizons, there are, in this context, two important notions. One is weakly isolated horizon and one is isolated horizon. But the main goal to give the big picture is to extract the minimal conditions for the zeros and first laws applied to the quasi-locally stationary horizons. And to see it, first, we want to introduce a non-expanding horizon on a 3 submanifold. And, oh, sorry. Yeah. And this horizon is a 3 submanifold, and on which there is an intrinsic 3 metric Q. And Q is the pullback of the full spacetime metric G AB to the three submanifold, satisfying the following condition. The first one is that the horizon is topologically S2 times R and is null. And second, the expansion of the outgoing null normals vanishes. And third, the minus contraction of the TAB and the null normal is future causal, which implies the null energy condition. So these conditions give rise to the property that the intrinsic metric on the non-expanding horizon is time independent. But to get the weakly isolated horizon defined from the non-expanding horizon, one need to add in one more condition, which requires the contraction of the derivative operator and the null normals become time independent. To get the weakly isolated horizon more stronger, to have the isolated horizon, one also required on the horizon for any arbitrary vector tangential to the horizon, the following relation will hold, which means that the full connection on the isolated horizon is time independent. And this condition gives rise to a very natural notion of isolation in the quasi-local sense. But most importantly, apart from the technical details, the properties of weakly isolated horizons and isolated horizons are first, defining conditions for the weakly isolated horizons and isolated horizons are all local on the horizons. Even the full forward metric is not assumed to be time independent on the horizon. For example, for a Castor-Tranxon solutions, which are symptotically de Sitter that admit even horizons, and there are no killing vector fields and no killing horizons, but the even horizons can be shown to coincide with weakly isolated horizons. And second, on those weakly isolated horizons and isolated horizons, we can locally define the surface gravity as interpreted as the acceleration of the null normal. So having defined this null quasi-local horizons, which categorize the equilibrium situation for the quasi-local geometry of black holes, now we want to have something in between that connects the two equilibrium situations. So for dynamical situations, when gravitational radiation and matter fields are pouring into a classical black hole, we need space-like horizons. As I said, this presentation is based on the 2004 work, but in the recent advancement work by Ashtaka and Krishnan, they generalized this notion of dynamical horizon to include the time-like surfaces. So first of all, I will point out that the dynamical horizon is a notion that is developed from the trapping horizon by Hayward. And the future outer trapping horizon is defined by Hayward in the following sense. It's a smooth 3D submanifold, and it's foliated by the marginally trapped surfaces S, so that the expansion of the outgoing null ray vanishes, and the expansions of the ingoing null normals or null rays is negative, meaning it's contracting. And the third condition is for the meaning of future, the directional derivative of the expansion of the outgoing null ray along the ingoing null normals is negative. And it can be shown that the future outer trapping horizons becomes null after equilibration. And in Ashton and Krishnan's work, to weaken the conditions of FOTH, one gets a dynamical horizon satisfying only D1 to D2. But physically, one can say a dynamical horizon is equivalent to a future outer trapping horizon, but the former is mathematically simpler. Again, I'm sorry, but in the work in 2005 by Ashton and Galloway, they show a remarkable unique result for the dynamical horizon. They show that a given dynamical horizon admits a unique foliation by marginally trapped surfaces. So that once a spacetime admits a dynamical horizon structure, it is unique. And this suggests, contrary to the parent horizon, that dynamical horizons are much more consistent and robust spacetime notion, other than the parent horizon I just discussed. So in sum, for the framework of a quasi-local horizon in terms of isolated and the dynamical horizon, both sets of notions are quasi-local, requiring no knowledge of spacetime as a whole. Rather, they are space-like notion per se. And both notions do not refer to the asymptotic flatness, meaning there's no need for ideal dynamical situation. Therefore, there's a preferable quasi-local framework of black hole horizon, which is not Cauchy size dependent and can be utilized to approximate the event horizon as a limiting case. But more importantly, we want to show that, well, on this framework, can we have like better understanding of the dynamic, thermodynamic laws for black holes? First, for the zeros law, actually, it can just follow from the definitions of the quasi-local horizons, for example, on the weakly isolated horizon. And it can be shown that the change of acceleration of the null normals on the horizon vanishes, so that the the surface gravity is constant on those quasi-local horizons. But this version of zero laws has some non-trivial properties. For example, the horizon is not assumed to be spherically symmetric. And also this zero's law holds even when the horizon is highly distorted and rapidly rotating. And it's generalizable to include electromagnetic fields. And I think the more interesting and more physically significant result is on the derivation of the second law on these quasi-local horizons. So on the one hand, the quantitative result of the area law can be easily derived following the conditions of these quasi-local horizons by showing that the extrinsic curvature, which can be used to track the expansion of the surface of the horizon on the cross-section. And because, as I said, the expansion of the ingoing null rays is negative, so that this extrinsic curvature is positive. But more importantly, the quantitative result is actually a very remarkable one. And this is the area's balance law on the dynamical horizon. So on this relation, it can be shown that if we have a dynamical horizon connecting two isolated horizons, which are the equilibrium states, and if we choose a small portion of the dynamical horizon, and we can derive some relations that connecting the left-hand side and the right-hand side of this relation. And on the left-hand side, R is a quasi-local function measuring the radius of the marginally trapped surface. And the I is a constant, it's the Gauss-Bonnet topological invariant, and it's positive. And on the right-hand side, the first term can be seen as the matter energy flux. The C represents the direction of energy flux. And the second term on the right-hand side can be seen as the gravitational energy flux. Because the sigma is the shear tensor and the zeta is some spatial space-like components of the shear tensors on the horizon. And it can be seen that the right-hand side of the first term of the right-hand side of the relation, if the cosmological constant is equal to 0 or larger than 0, this first term is always negative because the metric contribution is negative. So if the constant, the cosmological constant is 0 or larger than 0, the first term is always positive, and the second term is of course always positive. Then this is a so-called area's increase law. And also just to know that if one considers a quantum field theoretic framework on the curved space-time, the first term on the right-hand side of the equation can be negative because there's no energy condition, and which could cause the area to shrink. And as I said, this is actually a very remarkable result. As Ashika and Krishnan said, a priori, this is surprising that there should exist a meaningful expression for the gravitational energy flux in a strong field regime, where gravitational waves can no longer be seen as ripples on the flat space-time. So in order to test whether the second term on the right-hand side can be indeed seen as some quantity to track the gravitational energy, they test the properties of this term. They show that first, it is gauge invariant because in the construction and in the derivation, there's no use of any additional structure. There's no use of, for example, of coordinates or tetras. And second, they can show that the term can be shown that precisely on the marginally trapped surfaces has a positive value. And it satisfies locality, and it vanishes in the spherical symmetry because in that situation, the shear will be equals to 0. And it agrees with the calculation from the boundary flux. So they argue that interpreting this term as the gravitational energy in such a strong field regime is unproblematic, insofar as this term exhibits the properties typically expected of the gravitational energy in the asymptotically flat regime. And also on the weakly isolated horizons, a differential first law can be derived. To do so, one needs first to construct a quasi-local angular momentum on the quasi-local horizon. And the phi is the rotational vector on the field, on the horizon. And then one construct a time translational symmetry, T, in which B and omega are just constants on the horizons. Well, B actually, physically speaking, B can be interpreted as a scaling factor of the surface gravity, and omega can be interpreted as the angular velocity. But more importantly, they found that the necessary and condition for the first law or the following relation to hold if and only if is the condition that the time translational symmetry T generates a Hamiltonian evolution. So this gives a better sense of how the first law can hold in the quasi-local black holes. Of course, this first law, this relation can be generalized to in the presence of gauge fields, and in which situation it has the extra term, including the charge. And also for the simplicity, I didn't show the integral form of the first law on dynamical horizon because, for example, we have the balance law of the area, and we can also on these quasi-local horizons to have some balance law for the other terms, so that the first law has an integrate form if we work on the dynamical horizon. So summary for the black hole thermodynamics on these quasi-local horizons. For black holes, first, for black hole thermodynamics on the quasi-local horizon, the zeros first and second law can be defined quasi-locally and quantitatively. And the laws have the same expressions as those in the stationary black hole thermodynamics. And more importantly, black hole thermodynamics on these quasi-local horizons shed light on physical processes in which heat and work can be seen in a more physically significant sense, because we now have more quantitative controls of the forms of energy from different contributions. So that the second and third point in the argument are justified. With the quasi-local horizons, we can not only recover the laws of black hole thermodynamics, but also have a deeper understanding of their physical significance. So just go back to the main argument. I just show that contrary to Doherty and Calendar's survey, there actually exists a preferable framework of quasi-local horizons in terms of the isolated and dynamical horizons. And the thermodynamic laws and their interpretations are trivial on these quasi-local horizons. And more importantly, as we just discussed, the physical significance of these laws of black hole thermodynamics on the quasi-local horizons, they strengthen black hole thermodynamics in deeper and physically meaningful aspects. So my arguments here being supplementary to Wöhler's responses, I argue that they provide a fuller sense of black hole thermodynamics. But before going to the concluding remarks, let me mention a bonus point for quasi-local horizons. In response to Doherty and Calendar's second line of criticism against black hole thermodynamics, Wallace seems not to be very concerned about their worry, but tries to dismiss it as unwarranted. As he says that, but the concern that event horizon is a globally defined concept doesn't seem that relevant to black hole thermodynamics. So all black hole thermodynamics needs is a clear understanding of the horizon for the stationary black holes, and perhaps for holes that are mildly perturbed away from equilibrium, but pretty much all candidates' definitions for the horizon agree on the stationary black holes. Although I have argued that this concern from Doherty and Calendar provides a motivation for pursuing a framework based on quasi-local horizons, one that deepens our understanding of black hole thermodynamics and significantly supplements the stationary black hole thermodynamic picture. I wish to underscore a crucial merit of this quotation, namely the requirement that different definitions of horizons converge in stationary case, serve as a golden standard to assess the viability of any novel or reframed framework for black hole thermodynamics. And actually, the introduction of the quasi-local horizons paves the way for a better understanding of the approximate relations among different notions of horizons. For example, the framework of isolated and dynamical horizons meets this golden standard, as discussed above. And here's a very sketchy, intuitive line of thought. For example, isolated or weakly isolated horizon can be seen as a result of equilibration of a dynamical horizon. And the null quasi-local horizons were originally formulated based on the conditions of Killing horizons. And the Killing horizon can be understood as the asymptotic limit of quasi-local horizons under appropriate symmetry conditions. And similarly, the event horizons can be seen as such limits in light of the rigidity theorems by Hawking and others that link the Killing horizon to event horizon. But this is just a very sketchy lineup. But the more important result I want to show is between the render horizon and the quasi-local horizon, for example, the isolated horizon. When the first time I presented this talk, I think David asked me a question about the relation between the render horizon and those quasi-local horizons. And I think I screwed it up for the first time. And then I went home and I stood against the wall and thought of it. And I found that actually it's not hard to prove the following theorem, that the 3D submanifold be an isolated horizon satisfying the conditions for isolated horizon, then it can be proved that at each point on the horizon, there exists a coordinate neighborhood in which the space-time metric takes the form of the renderer metric up to the first order. And with this theorem, it's also not hard to see that the render horizon given by the renderer metric also satisfies the properties of an isolated horizon. And this means that a renderer horizon can be seen as a limiting case of isolated horizon, so that even under the quasi-local framework, the unruh effect can still be used to understand and interpret the thermal nature of Hawking radiation. Because the unruh effect is a well-studied effect, and it has many important relations to study the nature of Hawking radiation. And we have just discussed that Hawking radiation is a very important part of black hole thermodynamics. Therefore, we can still draw insights from Unruh effect to understand Hawking temperature within the quasi-local horizon framework without loss of generality. So a continuity, hence convergence, can also be found between a linear horizon and isolated horizon. And now let me go to the concluding remarks, in which I will just talk about some thoughts based on this work, which might be a little bit immature, but I want to draw some insights from the audience. The first point is that actually the framework of quasi-local horizons is helpful towards a deeper understanding of Hawking radiation. In black hole physics, the notion of dynamical horizons has been proven useful, although not yet entirely successful in deriving and understanding Hawking radiation in more fruitful ways. And the hope is that a deeper understanding of the nature of Hawking radiation will turn out to effectively justify and further support our belief in the validity of black hole thermodynamics. And also, the development of different formulations of black hole horizons has been shown to be a very long margin. We actually go from even horizons to trap surfaces due to the need to address some physical questions, for example, to see whether the global symmetries are really something that cause the singularity to exist. So Penrose, you develop the trap surfaces in order to address that concern. And then from trap surfaces, we show that apparent horizons can be constructed, and apparent horizons are actually useful in many contexts in the numerical simulations. And to overcome some drawbacks of the apparent horizons, Hayward proposed the trapping horizon. And as we see, the isolated dynamical horizons inherit the spirit of the trapping horizon as some quasi-local notions. And there's a recent work that tries to address some disadvantages of dynamical horizons during the time when dynamical horizons were still seen as space-time notions. Space-like surfaces. So Bosos and Egenhardt proposed a preferred holographic screen hypersurfaces to address these concerns. But now I'm less sure because the dynamic horizons can be shown to also include the time-like surfaces. But in any case, I think I mentioned this work by Bosos and Egenhardt for another reason, because many people might think Ashitaka is a little bit closer to like quantum gravity. And by showing this additional work, it can be suggested that the quasi-local horizon framework is more general than some specific contexts. And this brings me back to have a short comment on Doherty and Calendar's criticism. So on the negative side of it, on the negative side of the criticism, sometimes being too skeptical of physics will make us neglect the true and exciting development in physics. But on the positive side of it, I think their criticism successfully motivates philosophers to engage more with recent developments in black hole physics. And also, a different point I want to mention about this development is that the development of black hole physics has been very fruitful, but it's ongoing and far from complete. Nevertheless, I think this is another case in which grasping the conceptual continuity matters. It helps us to understand how to treat different notions of horizons approximately, and how to see the development of these different notions as addressing the same physical problem, etc. And lastly, I want to talk about additional concern. Although I think we have good reasons to keep the distinction between phenomenological thermodynamics and the statistical mechanics visible, but what if some working physicists take instinctively that to be a thermodynamic system is to be synonymous to be a statistical system. Well, this is complicated in black hole physics, but the very short answer is we can just wait and see how physics, especially the physics of quantum gravity, can tell us in the future about it. But here, the tentative answer, which is relevant in the context, is that I would try to argue that even in developing a statistical mechanical underpinning of a black hole thermodynamics, the framework of quasi-local horizons is still preferable. And in particular, in loop quantum gravity, isolated horizons allow one to treat the black hole boundary as the inner boundary with well-defined surface degrees of freedom. And this setup enables a consistent state counting framework, offering a microstate interpretation of entropy that is local to the horizon. And as I said, this is just some like immature thoughts. And with that motivating thoughts, I will just conclude my talk. And thank you, everyone. Should I stop sharing?
We have about half an hour for questions. Let's start on this end and work our way that way.
Hi, Yichen. Can you hear me?
Yes.
Yeah, thanks. So I get two related questions. I guess you probably like I'm gonna ask about like how is there a way to show like the exact killing field emerging from all these local times over from which the Hamiltonian is like, or like the locals or Hamiltonians are conserved? Also, is there a way to show the emergence of the exact killing field, global killing field, uh, yeah, in some kind of approximation or something? I guess I was thinking about in terms of like, the approximate killing field stuff that I was thinking about. Yeah, I was like, is there a way to show that? And if that's a development tool, right? Like if you could show that, then in some sense you do have the idea of an approximate killing field, and then you can go.
Yeah, interesting question. I mean, I need to confess first, I don't know. I'm not an expert on approximate killing field, but there are ongoing works by Ted Jacobson on the approximate killing fields. I mean, intuitively speaking, I think it could be a framework of quasi-local horizons to use it to discuss like step by step in which sense we can recover the killing fields, not only in the stationary cases, right, but also in more dynamical case. But I mean, to be very honest, I have no idea of the physical results yet, but I would say it's very interesting direction to go.
Yeah, thanks. And I guess related to the killing field thing, like I guess if there's no killing field, then the black hole as a whole, it wouldn't have a temperature, right? I mean, if temperature is related to, like I was thinking of the Tolman effect kind of situation where, if you have a killing field, then you have a global time and a global temperature attached to it. But if times, then I know that to talk about the Tolman effect, you need a background of global time. So maybe in this case, you can't even start talking about that kind of relation. But I don't know if there's something to say about that.
Right. No, so first of all, I think like to have a framework of quasi-local horizon doesn't mean that studying the stationary cases are not important. But on the contrary, I think the stationary cases are most important because that's what we study thermodynamics, at least the phenomenological thermodynamics of black holes, right? We want to have some sort of maybe not ideal, but some sort of isolation and some sort of discussions on the equilibrium states of it. But the quasi-local horizon framework to give us a more underpinning picture in which you can recover those stationary cases. It's not to say that, well, with the quasi-local horizons, we don't study stationary case. On the contrary, I mean, as I said, the weakly isolated horizon and isolated horizon are the more fine-grained notions of the stationary situations, right? So yeah, I mean, to have some discussion on like Tolman effect, etc. Of course, we can go to the stationary states, and if we don't like, if we want to just talk about the local temperature, we can just talk about, for example, the near horizon situations in which you can have control of this notion of energy.
Yeah, I guess I remember you telling me that you're deriving the tone effect in these cases before. So I was wondering that whether there's anything like related to how these local temperatures relate to each other in like the general quasi-local case, or maybe there's no nice relation yet.
Well, I mean, in deriving the Tolman effect, actually, it's been shown at least you can do that in the stretch horizon, right? And in most cases, as far as I know, that you do need some notion of stationarity on the space-time. So you have the Tolman effect.
Okay, yeah, thanks.
Well, first of all, thank you. That was a beautiful talk and reporting some very impressive results, I think. And progress on the understanding of the analogies between black hole physics and classical thermodynamics. I have a question about some suggestion you made, excuse me, along the way that I found intriguing, and I wanted to ask you if you could expand a little bit on that. And that is that I'm not quite sure how to phrase it right now, but you suggested that the consideration of these quasi-local horizons could shed a light on the distinction between heat and work, or more precisely on how the thermodynamic distinction between heat and work could be translated to a black hole setting in which a similar distinction would survive. Could you explain a little bit more how that is done?
Yeah, thanks. It's a very, very, very good question because I'm still keep thinking of it. But here are two thoughts I think I can share. First one is, as I showed that on those quasi-local horizons, you have some results that can have some quantitative control on the different notions of energy on the trap surfaces. Right? If we talk about some finite observer that could have means to interact with the black hole, of course, I mean, to some extent, it can be shown to be equivalent to the stretch horizon or membrane point of view, but it's a more like the robust argument. So that we can talk about the ways in which we have the resources to interact with black holes. And the second line is in more concrete language. In the paper by Wallace, he shows different ways of intervening, hypothetical intervening black hole. For example, you can talk about Penrose's process to increase or decrease the angular momentum of the black holes. But to put that into a more like quasi-local footing, I think it's also possible to talk about some hypothetical interventions as well as the control that we have more quantitatively on the different notions of energies. I think it's a very promising way to develop the further thoughts of how exactly can we distinct heat and work in this context. These are just a very like general thoughts because I still need to work exactly on the specific ways in which I can talk more about it. But thank you for the suggestion.
Thanks. You had a specific comment earlier that I wasn't sure I saw where it was cashed out, that one of the things the quasi-local framework would give us would be a way to talk about the angular momentum and other such quantities as associated to the horizon rather than as associated to spatial infinity. So normally speaking, I think of the angular momentum of black hole as something like the Noether current, the angular momentum current is infinity. I may just have missed a step, but can you help me through how that's happening?
Could you remind me which place?
Yeah, you said you commented asymptotic flatness in your setup of the problem, I can see certainly you're characterizing the horizon, the local horizon, but not via asymptotic flatness. I thought you'd suggested at one point that I could characterize something like the angular momentum of the black hole as a horizon feature rather than as a asymptotic feature.
Right. Yeah, it's actually very beginning. Anyway, so like this is something I think it's being discussed in Ashitaka and Krishnan's paper. I think it's subtle because in that sense you need to construct some symmetry, but all they suggest in constructing those symmetries, they say they are just local to the horizon, and they construct the phase space of it, and the phase space, in the phase space, they have some symmetries on the horizon, and they say that those symmetries, those vectors that generate symmetry, does not have to be have these global symmetries as well. So that in this sense, you can construct the angular momentum and the related motions only on the horizon, not even some very close neighborhood of that.
Okay, I mean, I'll explain my confusion, which isn't intended as a criticism. I just think there's something more to understand. Yeah. I mean, generally speaking, something like angular, I could probably do energy as well, but let's do angular momentum. Generally speaking, in GR, I would expect angular momentum to be somewhat non-local in space time. So I would expect there to be a well-defined angular. I've got some complicated self-gravitating system.
Yeah.
I would expect there to be a well-defined angular momentum at infinity because it's an inertia charge. But I'd expect and I'd expect to be able to find a inertia current that generates that charge, but I wouldn't expect that inertia current to be diffeomorphism invariant or tensorial, for the same kind of reasons we're used to for gravitational energy. And so I would expect that if I had, a bunch of black holes co-orbiting one another, that there'd be a robust, well-defined angular momentum for that system, which maybe in certain contexts could be approximated as local angular momenta for the individual systems plus a sort of an orbital angular momentum of the whole system. But I would be, surprised rather than astonished, but surprised to find that there was some robust distinction, an exact distinction that was locally characterizable between the angular momenta of the individual black holes and the joint angular momentum of the system of orbiting black holes in their mutual spacetime. So I'm not particularly expecting an instant response there, but it would be interesting to explore slightly more how much this is actually giving us a robustly local notion of inertia charges for these black holes, if they're not embedded in asymptotically flat space-time and isolated, but if I've got some interactive system of multiple such.
Right. Good. Thanks. That's very helpful. I mean, I would definitely think more about it. As I said, I mean, the result of the area balance law is already shocking to me, and I spent some time in understanding it. And this, you're concerned about whether there's a robust notion of the local or quasi-local angular momentum definition. I would definitely think more about it, and I cannot say more now.
Okay, thanks.
Thanks. Sorry.
Yeah, we've got Emily online.
Hi there. I apologize for the question being so basic, but do you mind returning to the slide where you define weakly isolated horizons? My question from the middle of your talk, which was quite premature, was basically actually like, how are you going to define equilibrium or unchanging if not by stationarity? So I want to make sure that I've absorbed this. Right.
Yeah. So in order to have some kind of stationarity, you have this I4 condition, and the I4B conditions are basically what constrains the horizon's geometry to be stationary.
Okay, taking a
it has
bit
some
longer to
control.
absorb.
Yeah, it has some controls on the development of the neural curves or neural normals on the horizon to regulate the behavior of the geometry. Yeah, that's the basic idea.
Okay, great. That's a great way of putting it. Great. Okay, can I ask one more question while I've got the microphone?
Yes, please.
And apologies if it's tangential, but I'm wondering, as someone on the front lines of this topic, what you and maybe the audience think about Eric Curiel's claim that black holes actually have temperature in the completely classical theory. Are you familiar with that?
I think there are better scholars to respond to this
Sorry.
question.
Who said that, by the way?
Sorry, what?
Who? Sorry, I can't see. Who said that?
Wayne has something to
I'm
say.
Wayne. Yeah. So Eric has been saying this for like am I in the camera? Here. Hi. Eric has
I can see you. Thanks.
saying this for a very long time, and every time I've seen him give a talk, there'll be something like, "Well, I think I can show blah 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 blah," and there's never ever been a calculation. But the claim is that if you've got two black holes in proximity with each other, they're going to exchange gravitational radiation and equilibrate and come to the same temperature. There's never been a calculation of that, and I think it's incorrect. The two orbiting black holes radiate energy out and merge, and there's no tendency to come to the same temperature before they do that.
I mean, it's obviously that violate the area.
Yeah.
I didn't catch that. I'm sorry.
David said, and yeah, right. Go ahead.
On some level, it obviously has to be correct. It violates the area theorem. So if I have it, if I can treat black hole, if I can treat a system of multiple black holes as thermodynamic systems interacting thermally, I need to be able to have situations where I have a decrease in entropy of one of the black holes, an increase of entropy of the other black holes as part of some kind of thermal cycle between them. We can't have that because the area theorem applies for black holes individually. So each black hole, so in classical general relativity, each black hole individually must have a non-decreasing entropy. So there can't be any process of transfer of that kind between them. There isn't a route for heat flow. I can only do that when I'm in a quantum field theory regime where I've got the Hawking radiation violating the energy conditions and so violating the area theorem.
Good point.
Okay, excellent answer. Thank you very much. I'm sorry that the question wasn't really directed at Yichen.
No, because
I'm glad. I'm glad you mentioned that because it keeps coming up, and as a referee, occasionally gets sent papers that refer to that as if it's like something that should be still taken seriously.
Okay, well, it's good to know. Thank you very much.
Okay.
And also thanks for bringing up this question.
Hi, Yichen. Thank you for your talk. It's very
Yeah,
interesting. I want to ask a clarification question, but just very basic about the earlier slides on the question about foliation independence and the worry about contextualism, observer dependence. So just want to clarify, do you think that this concern has been completely addressed in the quasi-local framework of horizons? Or do you think that's only partially because there's no Cauchy slicing dependence? Just want to kind of clarify on what is the status of that concern and how you feel?
Yeah, very good question. I've been thinking of it recently. So first of all, I think to some extent it's successfully addressed because of some forms of uniqueness theorems of the dynamical horizon. So that even it is foliation dependent, I mean, it's foliation dependent not by the Cauchy size, but by the marginally trapped surfaces. And there are some unique theorems that I show that guarantee the uniqueness the beautiful features of this dynamical horizon to be the unique structure once it's found. But I was thinking, well, sometimes uniqueness theorems in general can give us some sort of robustness or some sort of consistency. But I was looking for some stability theorems specifically about how, if we perturb these dynamical horizons, or even in some situation it goes to line up with the apparent horizons, whether those results will still hold. So yeah, I think So the answer is, on one hand, I think the uniqueness theorems do give us a lot of information about why the concern about foliation would not carry over to the the quasi-local horizon. But on the other hand, was looking forward to see more results on the framework of quasi-local horizons to show exactly the stability as we commonly construe, to show that the dynamical horizons could have better properties, or maybe they don't, but there could be further notions of quasi-local horizons that come up to address these disadvantages, if there were any. Yeah.
Just to clarify, the first concern is addressed by the uniqueness result, but not the second one. Okay. Thanks.
Thank you. Could you say a bit about how much you're using the Einstein equation in these
Oh,
results?
yeah. So in deriving the second law, Einstein equations are used, of course, and it's used in the initial value formulation form because you need to input the scalar and the vector constraints to develop the dynamical equation portion, and then you have these results. So I think in general, the zeros and first law are defined. Sorry, the zeros laws is defined following the conditions, and the second law of the quasi-local horizons, they definitely use Einstein field equations. And in the first law, I don't think they use it. They just study the geometric properties of the quasi-local horizons and construct those relations between these quantities.
I mean, the context of the question, and then because this is again a thought for further work, really. I mean, we have some reasons to want to study general diffeomorphism covariant actions. I mean, coming from effective field theory, coming from string theory. And last time I looked at this, which is when I wrote the paper you were kind enough to refer to, then as I recall, the quasi-static bits of the story largely generalized to arbitrary diffeomorphisms of covariant Lagrangians. So we have the Wold offers a general definition of the entropy as the horizon Noether charge, and we have a statement of the first law with respect to that general result. And I believe we have quasi-static, like perturbative derivations of the second law in the kind of thermodynamic regime, where I take a stationary black hole and I perturb it slightly and demonstrate the entropy always goes up under the perturbation. As far as I recall, there's not a generalization of the area theorem, which, as you say, the Hawking area theorem does use the Einstein equation. As far as I recall, there's no kind of full sort of generalization to the sort of full num quasi-static case there. So in the context of my question, I was just wondering what part of the framework you're developing here counts as sort of generalizing that fully, arbitrary diffeomorphism covariant Lagrangian, and which bits of it are sort of more along the lines of Hawking's result, where we're generalizing, but in the context of the Einstein equation. I mean, look, the Einstein equation obviously has to be the correct equation in the infrared limit, so it's not exactly a sin if general results we establish in non-quasi-static contexts rely on the Einstein field equation. But it would be interesting to get some
good. Yeah. Right. This is very, very deep concern. Right. So I think you are right to point out, well, it's a crucial issue to discuss how much Einstein field equation is used here in consideration of toward quantum gravity. But I don't know yet, like in what kind of thought in the recent development of quasi-local horizon. I mean, there definitely are many, but maybe due to my ignorance, that using this kind of framework and going toward some more general framework is feasible or not.
I mean, it wouldn't entirely surprise me if these ideas are coming out of the kind of Ashtekar group. It wouldn't surprise me if they're more tied to the field equations than some approaches. I mean, the loop quantum gravity approach has generally worked very much inside the context of the Einstein equation and taken it more seriously than the
exactly
tradition coming out of quantum field theory.
Right. I mean, this is definitely exactly the same question I want to do, because in the end I mentioned if we want to use this quasi-local framework to work in the statistical mechanical context, then we need to employ a lot of knowledge from, for example, quantum gravity to reduce the reliance on the Einstein field equations. But as much as I know now, I cannot really give a very satisfactory answer. But I will report to you next time.
I mean, again, it was a thought for further development of the project rather than any problem with where you are.
Yeah.
Thank you.
But thanks. This is a very, very deep concern. Yeah. Well, a suggestion.
Hey, Yichen, you mentioned in the end of the talk about the microstate counting and the quantum gravity. Could you say a bit more about that? I just want to hear, is that the general result or just particular about loop quantum gravity, and how does that work here?
Oh yeah, the result I was referring to was actually a particular way of counting, let's say, microstates in loop quantum gravity. And one of the motivation I wanted to do that is that in David's paper, he discussed different approaches to do the statistical state counting in low energy gravity, in ADS-CFT, or in string theory. But I think no matter your opinion about those approaches of quantum gravity is to have some discussion in loop quantum gravity, which I think is a good theory of black hole. It would be helpful to the community. And so to be more specific about what they are doing there, so they have this quasi-local horizon in as well as the so-called Chern-Simon theory, so that you can use the quasi-local horizon as the intrinsic geometry locally to truncate the quantum states of space-time on the boundary, so that you get a sense of how to count how many states are there on the boundary.
Yeah. Which paper is it? Could you say again?
Sorry?
Which paper was it that they had this result about microstate counting?
I think Alexandro 2017's paper is a good one. Let me check the title of the paper, but I can send you. Yeah, I can send you.
Thanks.
Yeah.
I actually had a quick question about that. Which is there actually a reason to think in this context that there will be a relationship between entropy? So I suppose black holes are generally thermodynamic systems, right? Is there a reason to think that the arguments that we have for more ordinary statistical mechanics systems, the arguments that we have that they're for a relationship between thermodynamic entropy and state counting are actually going to go through this contest? So any reason to think we should be counting states in order to get an entropy in a statistical context for black holes?
Yeah, good question. I think it's a way of understanding better the interior status of black holes. It's more like a concern on that part, and also.
Yeah, I was just really interested in the relationship between state counting and entropy. Like, do we have a reason to think that extends to this context? Because if I think about the arguments for the relation, they imagine, I imagine, they involve things like, connecting a system to a heat bath and manipulating it in various ways, and using assuming that you've got a canonical distribution for the heat bath and you've got unitary evolution of the whole thing, And the question is, do those sorts of arguments, can they be extended in a straightforward way to this to black holes? And David had a finger, so
yeah, I mean, my thought would be something like this. If you were going to argue for it, you'd probably go from the sort of local thermodynamic equilibrium frameworks. If I've got a system where its individual parts have equilibration timescales very fast compared to the scale to the evolution changes of the larger system, you'd normally expect to be able to treat the system as locally in thermodynamic equilibrium and assign, state counting entropy in the usual way. Now, if the StatMech reading of black holes is right, then your system is something like the stretched horizon, and the short range degrees of freedom here are Planck scale, and you'd expect them to have an extremely rapid local time equilibration, much faster than the sort of gravitational, astrophysical time scale on which the black hole would be evolving. So that would be my sort of hand waving reason why I probably would expect that.
Okay, thanks. And actually, that might be. It sounds like the argument really isn't out there in the literature, so that might be a nice avenue for future work for somebody.
Yeah, thanks, David. Thanks, Wayne.
Okay, thank you, Yichen, and we're gonna let you go. It's 11.
Can I just follow up with David's comment?
Sure.
So just your comment and your answer to Wayne's question. So I think it's a very good comment. And so in this sense, if we have a statistical mechanical underpinning of the black hole thermodynamic system, we can not only discuss the recovered like the Birkenstein bound in more quantitative way, but also we can talk about the equilibration as you just discussed. Is that the right way to understand it?
I think so, yeah. I mean, I was slightly thinking aloud, but the thought is that even processes that look really fast from an astrophysical point of view, like black hole collisions, are going to look extremely slow compared to the kind of equilibration time of the supposed Planck scale microscopic degrees of freedom that are making up the stretched horizon. And so that's exactly the regime where you kind of expect to be able to treat the system as instantaneously at local equilibrium,
Right.
and so apply thermodynamic quantities that are space-time dependent, but still definable, and which you could still give a local microphysical description. So if you imagine some little square of the event horizon, which is large compared to the Planck length, but small compared to the size of the black hole, which gives you quite a lot of room to maneuver, then
Right.
you'd expect that region to be instantaneous at equilibrium on timescales short compared to the timescale on which the whole horizon is evolving. That was the thought.
Cool. Right. Good. Thanks. Thank you very much.